Okay, so now I want to have some discussion about congestion pricing and how that relates with cost modeling and average cost and marginal cost. First of all, let me ask you this question. If somebody says the term congestion pricing, what does that mean to you? What does congestion pricing mean to you? Pause the. Yes, so some good responses here. Congestion pricing, in some ways, accounting for how much time and money you're losing when you sit in congestion, as everybody drives their own car, their own vehicle. How much time and money are we losing? What kind of externalities are we imposing on other people by being traffic? And you know, everybody hates traffic, but it's a big realization for everybody that when you realize that, you know, you're not in traffic, you are the traffic, right? So congestion pricing, you can think of that as congestion pricing is a way to remind people that you are not in traffic, you are the traffic, okay? So that means that when the roads are congested, you pay money, you pay more money to use the road. And then when the roads are empty, then maybe you don't pay as much money to use the road, or maybe you don't pay any money at all to use the road. And this is something interesting, right? Because we use pricing as a signal for so many things. Pricing, the use of prices as a signal is absolutely, you know, very commonplace. Everybody uses it. You know, anytime there is some scare with regards to gasoline, the gas becomes more expensive. Anytime, you know, you recall, I don't know, 2020, the toilet paper crisis that we went through, not exactly a crisis, but the idea that, you know, when there was demand for toilet paper was really high and how expensive it had gotten back then, right? So, and that basically provided a signal both to the consumer that, hey, you guys might want to save toilet paper. I don't know how you do that, but maybe you don't want to buy as much. And then on the other hand, it was a signal to the supplier that, hey, you can get good money for it, better bring some quantities to the market. And obviously it's not as simple as that, but all I'm saying there is that we use pricing as a signal to both consumers and manufacturers, for consumers to demand less, for manufacturers to produce more when the price rises. But for some reason, the way, and I think this is because there's so much entitlement around being able to drive, that we have never been able to price congestion in the same way. Even in New York City, which you think like very progressive place or whatnot, they're having trouble introducing congestion pricing because of political issues there. So congestion pricing is a very hard sell politically, even though we accept pricing as the mechanism for as a signal for both consumers and suppliers that, hey, some resources are really scarce, but we can't do that to the road. We keep paying the price in terms of the time lost on the road, but we can never price it appropriately. And that's partly because we have this sort of almost an entitlement type mentality around being able to drive without paying anything out of pocket, even though we are paying the costs in a lot of different ways. But the minute you talk about congestion pricing, charging some dollar amounts to be able to use a certain road, things get plenty dicey. And that's not to say that congestion pricing is nowhere implemented. I mean, we have that on toll roads. I think in Seattle, we have pretty pure congestion pricing, where maybe not exactly pure congestion pricing in theoretical sense, but pretty workable congestion pricing model where they have basically a base toll, and then that toll changes in real time based on real-time traffic congestion. I'm familiar with that, and I've used that as early as 2013. I recall using that toll road in Seattle, and I know we have that on the Bay Bridge. You know, the price changes depending upon where you're going, and and how much congestion there might be. Although it's static in nature, it's basically a time of day type variation. But still, the idea is the same: is that at the times of day where there's more congestion, you pay more. But still, there is a lot of political opposition to it. But the idea itself is actually based on proper accounting of the cost that you impose on society by being the traffic. Not by being in traffic, but by being the traffic. Okay, and let's see how that works out. What's the theory of the average cost and the marginal cost issues that you just dealt with? How does that theory play into it? Okay, so let's look at that question. And I'm going to go back to a very, very basic sort of example where you have an origin and destination, and you have some travel demand associated with that, and you have some travel demand associated with that. VA and VB is the demand on each link, and you could have different demands. Okay, so it's not like that you have a fixed demand. That VA and VB just represent how many people are using link A or link B. How many people are using it at any given time, and that could change. Okay. And then this is hourly demand. And then this is what I'm showing you here. VA and VB is the hourly demand. And let's call ACA and ACB, the average cost on link A and average cost on link B, to be the user perceived link cost function, which behave like this. Okay, and you see that as V increases, the average cost of V goes up. And this is something that I've talked to you about before, even in this class, and definitely in CE 321 as well. That's the idea of the link performance function. Does anybody recall from one of our previous discussions, what does link performance function stand for? What does it do? What does the link performance function do? I'll pause the recording and give you a chance. So the link performance function essentially describes what happens to your travel time. What happens to your travel time as you increase the number of users on the road. And you can think of this as, and it's surprisingly related to, or similar to, you can see the analogy here. It's surprisingly similar to, the cost function that we saw in the context maybe of manufacturing, that you have a fixed cost. And then as you add more cards or build more cards, or as you build more widgets, your cost goes up. And that sort of is exactly the same thing that you see. If you only have one car on the road, that car is going to spend some time traveling that link. So if it's a, whatever the free flow speed is, depending upon, so you can think of this item, or this portion of the curve. You can see this portion of the curve. Okay, so this portion of the curve. You can see this portion of the curve right here as my fixed cost. This part of the curve is my fixed cost. Okay, and then even if there is nobody on the road, so this is sort of your free flow travel time up to here. And then as more people get added to it, the travel time first rises slowly and then rises very fast. So that sort of describes the cost function of being on the road. Okay. So that describes the cost function of being on the road. And then, so you could see that this is what we call the average cost function, because you're describing how much travel time one user will take how much travel time one user will take given V people on that particular link. Okay, so that's what we can call average cost of driving on that link. And average cost is, if there are more people on the road, the average cost does increase. So if there are this many people on the road, you'll have this average cost. But then if there are higher number of people on the road, then your average cost becomes higher. And then in CE 321, in our fundamentals of transportation engineering class, we also learned the user equilibrium principle, where we minimized the average cost, because the idea is that every user will try to minimize their travel cost, right? Every user will try to minimize their travel cost. And how can, if there are two links, how can a user minimize its travel cost? How would you select a route if you were trying to go from your origin to your destination, and you had these two options, link A and link B, and you were trying to minimize your average cost? How would you choose link A versus link B? What do you think? So what I heard from you guys is that, yes, you agree with the approach that, yeah, as a user, to go from origin to destination, you'll choose link A or link B such that you minimize your travel time, right? So if you can minimize your travel time, you'll choose link A. But so maybe if you're the first rider or first driver, there's nobody else on the road, you will choose the link with the lowest amount of free flow travel time, right? If both roads are empty, link A and link B are both empty, but they do have some sort of fixed cost. They do have some fixed cost. So you'll pick the link that has the least amount of fixed cost, right? So you'll go on that road. But as some drivers choose that road, what would they do? They will increase the volume A. Okay, let's say link A had a lower free flow travel time. So initial people, starting people, when both roads are empty, they start to pick link A. Then what will happen on link A? What would happen to travel time on link A? If some initial people, because they chose link A because link A had a lower amount of free flow travel time, if people start to pick up and start using link A, what would happen? The travel time would rise is what I suspect would happen. And then, yeah, link A will become congested and the travel time will increase. And then it'll keep increasing until you hit the link B's free flow travel time, right? But once it goes above link B's free flow travel time, now people will say, hey, to heck with link A, link B is the one that has shorter travel time. So I'm going to go choose link B now. Now people start taking link B, and now link B will become congested, and then people will switch back to link A. And this will keep happening. People will, like, as more people get added to it, they'll keep switching routes to minimize their travel time. But at some point, an equilibrium might exist, and we call it the user equilibrium. What do you think would be the condition of that user equilibrium? What would be the condition of user equilibrium where everybody knows which route they should pick and they just go and take it? What has to happen for that equilibrium to exist? Thoughts on that? What has to happen for you under this scenario to achieve user equilibrium? So I'll go with the one response that I got, which is the right one, is that at any given demand level where the equilibrium has to come, the equilibrium will happen when, at any given demand level, when the travel time on both links become equal, right? If both routes are being used, when the travel time on both routes become equal, exactly the same, that's when what will be the equilibrium, because there is no point in switching routes anymore because both routes give you the same amount of travel time. So what are we saying here is that in this scenario, there's no point for you to switch routes, and that's where the equilibrium will happen. So you can then solve for VA and VB by saying, okay, if the average cost on route A as a function of VA and average cost on route B as a function of VB, VA and VB being the respective flows on each route, if those two average costs are equal and my VA and VB add up to the total demand, I can then apply these two equations. I can then apply these two equations right here, where ACA and ACB are equal, and then VA plus VB is equal to the total demand. Okay? And then we solve this type of problem, like user equilibrium problem, for a simple linear model in CE 321. We don't go multiple routes, but we do solve this problem. We do solve this problem in CE 321. Okay. So let's see. Okay, so let's see what happens then. And then you could also then figure out, the total cost, travel cost on the network though. So what I'm trying to get at here is that this is the approach that people will take if they left to their own device. If they're left to their own devices, they'll try to minimize their average costs. Okay. And then, but if you want to minimize the total system cost, the total system cost will be that you take the average cost on route A, multiply that by VA, so that you get the system cost for all travelers. So this expression right here, gives you the total cost on just on route A. And then this expression gives you the total cost that is being spent, or total, and cost and travel time, I'm using that interchangeably here. Okay, so costs are basically travel time. So if everybody is taking average ACA travel time, and then there are VA users, their total travel time is VA times ACA. You add that to VB times VCB, you get the total cost. You get the total cost on route A plus route B. And if you want to minimize this, okay, as a function of VA and VB, you take the derivative with respect to for route A with respect to VA. This is the derivative you take, and then you set that equal to 0 basically. So then this is what you will get. So that when marginal cost of route A, and then remember, the derivative represents, if I want to minimize the total cost, I take the derivative with respect to route A and route B total volume and equate that to 0. And then, but remember, what does this expression represent? What does DTC over DVA represent? The derivative with respect to the volume. What does that represent? You should know this from the homework problem that you just submitted today. What does the derivative of total cost with respect to volume represent? So some good responses there. I got 3 of them correctly. The derivatives, these individual derivatives with respect to the volume being used on each route or volume being pushed on each route, they represent the marginal cost, right? So this is the marginal cost on route A. The left-hand side of this equation is marginal cost on route A. The right-hand side is the marginal cost on route B. So that means the magnitude of marginal cost, because remember the total volume is fixed. So if you marginal cost on route A has to be negative of the marginal cost of route B. Means like if I add one more vehicle on route A, I'll be subtracting it from route B. So that's why the negative sign. But the idea is that if the marginal cost magnitude on route A is equal to the marginal cost magnitude on route B, that's when I'm able to minimize my total system cost. So as a system planner or a system engineer, this ought to be your goal. Is that you don't want big drivers to minimize their average cost, but instead, if they could minimize the marginal cost, or I'm sorry, if instead of equating the average cost on each route, if the marginal cost on each route were equal, and drivers divided themselves, the users divided themselves on the network this way, if the marginal cost on route A were equal to marginal cost on route B, like we saw here through this derivation, then we'll be minimizing in the aggregate the total time spent on the network or total travel cost on the network. Okay. Any questions about this? Does it make sense to say when the driver minimizes their average cost, they're minimizing their individual travel time. But if you want to minimize the total system travel time, instead of average cost on both routes being equal, like the case is in the user equilibrium, if you want to get a system optimal state where the total system travel time is minimized, instead of drivers trying to equate their average cost on both routes, the marginal cost on both routes has to be equal. Does that statement make sense to you? I want not the average cost on both routes to be equal. I want marginal cost on both routes to be equal. Does that statement make sense to you? Any questions about this? So, the thing is that drivers are not necessarily worrying about average cost or marginal cost and all that. They're just trying to minimize their perceived cost. And if there is no toll at all, their perceived cost is whatever travel time they're spending on the road. So they're trying to minimize that perceived cost. Now the trick is, as a system planner, the trick you're trying to pull off as a system planner is that what if their perceived cost of the drivers, what if the perceived cost of the driver was not their average cost? What if their perceived cost, what if the perceived cost of each link was such that they were equating marginal cost on both routes? Okay, so that the drivers were making sure that they were placing equal burden on both routes by choosing their route. So what we do is, that's why we introduce what we call the congestion pricing. And then the congestion pricing that we introduce is defined by this, the equation that I'm just highlighting. The congestion price that I want to institute on each route is MC minus AC. Okay. So now think about this. If there were no congestion price, so let me try to type something up. In case of no congestion price, what is the perceived cost of route A? Let's deal with route A, or any route really. What is the perceived cost of driver of using that particular route? It will be average cost, right? Okay. In case of no congestion price, your perceived cost is AC. For any route, perceived cost on route A will be ACA, perceived cost on route B will be ACB. Okay, and then the drivers are basically trying to minimize their perceived cost. So that's why they want perceived cost on both routes to be equal. Now, let's see, in case of congestion price CP if I'm adding a toll, which is congestion price CP, the perceived cost would be what? Okay, I'm going to pause and I want you to answer it. Recording here. So I got some good responses here, some good questions as well. Is that there was some confusion around marginal cost. So I'm saying, don't even worry about the marginal cost just yet. All I'm asking you is that if you're assuming that they are in the same units, either in terms of travel time or dollar amounts, so there's no unit confusion, and they're all measured in the same units. If there was no congestion price, so you're not paying any toll or anything like that, then your perceived cost is basically that you're trying to minimize is the average cost. It's the time that you as a traveler, as one traveler will take from your origin to your destination. So any link that has no toll, your perceived cost is always just the average cost, right? It's the cost that you're incurring by traveling on that road. Okay. Now, suddenly somebody comes along, some pointy-headed planner or whoever like us, they come along, we come along, maybe the travelers come along, or the travel planners come along, and they tack on a congestion price CP. Your perceived cost won't just be CP though, right? Yes, you're going to be paying that out of pocket, but you have another component of the cost, which is AC, the average cost, right? You still have to travel on that link, so you're going to pay that price of travel, but now you're being tacked on the CP. So your perceived cost now is CP plus AC. Okay? Now, as a traveler, because as a traveler, you always want to minimize your perceived cost. So as soon as that CP gets tacked on, now your tendency is that, okay, I'm going to minimize, and then let's assume that both routes have toll and their average cost. So what your goal will be now to minimize that highlighted thing, that CP plus AC is what you want to minimize now. So this is what you're going to be minimizing now, CP plus AC, because that's your perceived cost. And now, all of a sudden, if route A and route B both have their tolls, and I'm going to write those tolls down. So remember, I'm not even worried about this right now. So my perceived cost, and let me write down these perceived costs on both of these routes, okay? So I'm gonna, so if your perceived cost is now CP A, and I want to make a CPA plus ACA. So your route A perceived cost is CPA plus ACA. And then your route B perceived cost is CPB plus ACB, right? And then assume that the small letters are subscript, okay? I can't quite make the subscripts here, but this should still work. Now, this is your perceived cost. Now, what would that equilibrium look like if these are the perceived costs on route A and route B? Remember, drivers are always trying to minimize their perceived cost, so they will keep switching routes until their perceived costs were equal. In the case of no toll at all, their perceived cost used to be AC, but now in the presence of toll, the perceived cost is congestion price plus the average cost. Now, what would the equilibrium look like in this scenario? What would the equilibrium look like if these were the perceived costs? What has to happen to these two costs on route A, these two perceived costs on route A and route B, which is congestion price of A plus the average cost of A and congestion price of B and average cost of route B. And then the non-capital letter is a subscript. Okay, so I'm going to just write down here the non-capital letter are subscripts. Okay, so think of these as subscripts. What has to happen to these perceived costs for equilibrium to be established? I already see a response, which is good. They equal. Yeah, that's it. Bingo. So what has to happen is that these has to be equal. Okay. Now, you don't want to price your congestion willy-nilly, right? You don't want to price your congestion willy-nilly. You already know, you already have some idea about what you want the end result to be, because your total system is minimized. Total system travel time is minimized when marginal cost on these routes are equal. Okay? So you want the marginal cost on route A and route B to be equal in magnitude. So what would you like? What would you like this number to be? Oops. What would you like? So so my question to you is, because you want these numbers to be equals. So we know that drivers are going to try to make these perceived costs to be equal. So as a planner, what do you want this to be? CPA plus ACA. What do you want it to be? You know that if these were marginal costs, the perceived cost of the drivers were in fact marginal cost, it will minimize the total system travel time. So that's why this is what you want as a planner. You want the sum of CPA plus ACA to be MCA. You want the sum of congestion price and the average cost on route A to be the marginal cost of route A. And then you want the same thing for route B. You want CPB plus ACB to be marginal cost of route B. Okay, so I'm gonna move it here, right there. This is what you would want. Does that make sense? That you want this perceived cost to be perceived cost plus average cost summation to be marginal cost of A, so that the drivers, when they try to minimize their perceived cost, they end up getting you to that system optimal condition that you had cooked up before. If you do this, if the drivers do this, they try to minimize their perceived cost, and you know that the new perceived cost of nothing but marginal cost. So that's when the drivers will end up doing this for you. The drivers will end up doing this for you, and that will be the best thing for the system. Okay, so with this equation now, CPA plus ACA equal to MCA, you can derive what your CPA ought to be, what your congestion price has to be. So this is where the equation, this equation comes in. This is where you know that the congestion price that you want to charge on any link has to be the difference between the marginal cost and average cost. So that's why CPA would be MCA minus ACA. So you could use this to then derive CPA. So that means CPA would be equal to MCA minus ACA. Okay? This is why congestion price. So what I'm doing is essentially rearranging this equation right here. So all I'm doing is rearranging this equation to estimate what CPAs are to be. CPA has to be marginal cost of A minus average cost of A. And this is that equation. So if you can charge the toll or the congestion price equal to marginal cost minus the average cost for both links, then you'll be golden. Then the drivers, while trying to minimize their perceived cost as they see it, they will end up minimizing the total system travel time cost. And those will be minimum travel time for everybody and the aggregate. And that's what you want to achieve. Okay, any questions about this? I know it's kind of a little bit complicated stuff, but I really appreciate, and that's precisely why I would appreciate any questions you might have.